Hello everyone, I am Eugene and my colleague Victor. We are from OsmAnd. It's an application for offline navigation and for offline maps. At this year, OsmAnd celebrates 15 years, and at this moment we have 2.5 million monthly active users across all platforms, over 100,000 daily active users, and more than 20 million installs worldwide. Over the past 2 years, when we were in the Richmond in 2023, we introduced significant new opportunities, some of which are highlighted here. First, our vector maps contain clickable trails on the map. User can click a trail to view its info, altitude, profile, distance, and start navigation. Next, we added an animation mode to our forecast feature, which allows the user to download 10-day forecast for offline use. The next, we made good progress with widget panels, enabling full customization of size and screen placement, as well as button layout, allowing for many actions to be implemented directly from the screen. We enhanced our 3D terrain maps, now available offline for all countries. Additionally, these compact maps generate hillshades, slopes, and altitude data, and include customization color palettes. 3D tracks. OsmAnd now features 3D GPX track visualization. This feature allows users to customize wall and line color based on GPX track data, making it useful for analyzing tracks in activities like paragliding. For me, I use it for my cycling. Popular places. It's one of the newest feature, while it allowed for Android and for web platform. This feature showcases trending location and based in Wikimedia and Wikipedia and Wikimedia data, enhanced with image icon on the map for easy identification place. And the context menu of these places includes a photo gallery. US maps, yeah. After our last visit, the USA, in 2023, we understood the need for edit of additional map data, especially for the US. And we added Tiger data to our offline maps and developed the US Maps plugin using US Maps sources generated by our backend team. And this plugin is experimental, but available for testing. You can use our link to our Reddit page. And our web platform, totally web platform upgrades during this year, and now it's featuring road planning, search, popular places, weather, road builder, and more. And it connects all our platform through a unified user cloud account. Fast routing, Victor?
Yeah, one of the most demanding feature was to improve the speed of the routing, and of course we were working on that main topic of presentation, technical side. But mostly, and it was a very demanding feature to get it really fast, the routing. Mostly applications use two kind of algorithms, A-star algorithm, which is very powerful, very flexible, but very slow. So basically, you cannot build a route in a reasonable time nowadays using OpenStreetMap data, like 100 miles or longer. And another one algorithm is contraction hierarchy, which is extremely fast, but has lots of limitations, which I mention later. So originally, we've been using A-star two-phase algorithm, and it was good up to some point, but it anyway has pretty much the same limitation of how much could we process in terms of speed comparing to A-star. We used the base graph, and another thing, it was not always optimal because we were using heuristics to basically get it faster. So it's 10 times faster than original A-star, but still not what we expected and slower than contraction hierarchy. So we get back to the table and looked at the highway hierarchy, developed, and now it's 4 times faster than two-phase algorithm, and sometimes it's 100 times faster than original A-star algorithm. So the challenge for us was, before we started developing the new algorithm, that contraction hierarchy didn't fit our requirements. First of all, we had lots of routing profiles, lots of dynamic parameters. We have also live data, and people could specify some specific points, which roads they want to avoid, and that doesn't work really great with the contraction hierarchy algorithm. Also, you can build for each parameter a layer, a profile, but it's just a huge amount of data. All our maps around the world, it's just 160 gigabytes of data, and each contraction hierarchy profile, it's 200, which is quite a lot and not reasonable, especially if we want to support dynamic parameters. And one more requirement was very important for us, that we support frequent updates, like 10-minute updates, and yeah, it's not feasible with contraction hierarchy. So the idea, we get back to the father of contraction hierarchy, it's a highway hierarchy algorithm, and we need to simplify the routing graph by contracting vertices. And the main idea was, okay, how do you contract it? And we took a look at this example. You have a large parking lot, and you know that there are only few exits. So it's natural that you remove all the edges on the parking and leave only the exits of the parking and connect with the shortcuts. Okay, but that's easy to say than do. How do you identify what is a parking exit, which is sometimes not trivial? So one main idea is to use like a flooding technique, when you put all the sources of the water stream outside the parking, and you put the sinks inside, and you see where the water flows. And when water gets stuck, like its limit, this will be the border points and the parking exits. If you not do it correctly, you will get a shortcut explosion problem. So if you, basically, you have a 2 billion vertices originally in the OSM graph and 2.5 billion edges, but the edges in a full graph grows by a square law. So even if we do it randomly, and we did it in the beginning, for 1 million vertices, you can end up with 1 trillion edges, which is quite a lot, which is really a lot and not feasible to build any routing. So in our algorithm, we ended up with 3 million points, simplified graph, and only 90 million shortcuts, which is extremely important, and that's how we get the tiny maps in the end. So how did we do it? Once again, but a little bit more on a technical level. So you start with a random point anywhere, you run the Dijkstra algorithm to a depth, let's say 100, and that's how you find the sync points. Then you run again, continue running Dijkstra algorithm up to level 1000, and the border points will be source of the water. Then you run a really great algorithm, Ford Falkerson, and that will find the maximum flow that could go from source to sink. And what is great about it is that you can also find the minimal cut on the graph. And the minimal cut is exactly the points of like parking exits where you want to put these border points. You repeat the same algorithm more and more for all points, and that's how you end up with the border points. Once you have the border points, you can start calculating shortcuts. The really good thing that they are, when you are building the graph, you don't really specify any parameters like avoid ferries, fast road, and so on. So you only specify parameters when you calculate the shortcut and you store it. So you can calculate as many kind of layers as you want, but we ended up with 2 in order to save memory. But also I will mention why 2 is enough. However, parameters combination also explodes. Like if you have 10 switches, it's a 2 power of 10, it's 1,000 combinations of them. And how it works then, we are ready to ship these maps to device, and that's how it works on device, the algorithm. So basically, you have a start point, end point. You need to identify in which cluster do you live. So you find all the points, like this green rhombus dots. This is a start cluster. And end with a Dijkstra algorithm. Then you build, because you already reached the second level of highway hierarchy, you can build from these dots based on shortcuts. This is straight lines. So you just build the route and find it. It's optimal. But then you need to refine it with a detailed graph, because we don't store geometry in order to save space, but also in order to apply dynamic parameters on the fly. So when you have a shortcut, we know, okay, from this point to this, we build the route again. And surprisingly, it works really fast, or fast enough, because we don't store, but we also have lots of benefits, because we don't have we don't store all the geometry. We save disk space and basically network as well when people download the maps. But we also can apply dynamic parameters. So for example, if person avoids the roads, we could apply it on a third step. And if cost of that shortcut originally that was stored changed a lot, then we can apply and recalculate, get back to the second step and recalculate it again. So we have some reiterations limit, like 50 or something, but usually it's enough to do 1 or 2 calculations on average for lots of parameters. And that's how we achieve a win-win situation, that it's still fast, but it works with dynamic parameters. And in that, that's what are the main benefits. So we fully customized. It's a tiny footprint. We support regional maps. And we able to support frequent updates, like 5–10 minutes update to offline maps. The only downside, the biggest one, that all your maps, base maps, and not the live which you apply on top, needs to have the consistent version. So if you download it one state in November, then the neighborhood state which you are going to travel should be also from November. Otherwise, they just have a different graph, and that's, of course, limitation. That's it. Thank you.